Okay, so it's really a great pleasure to welcome Lenka Zdeborová to Kempner Center Studios today. Lenka is a professor of physical and computer science at the École. So she leads the statistical physics and computation laboratory. Lenka's research has been enormously influential. Her work is at the true interface of statistical physics, machine learning, and high-dimensional inference. It has shaped how many of us think about learning, optimization, and complex systems. Brief bio: before joining EPFL, she received her PhD in University of Paris Sud and Charles University in Prague at the same time. Not sure how that worked, but congratulations.
It's a program.
The postdoctoral position at Los Alamos was a researcher at CNRS and Saclay. She is recipient of many awards, including the CNRS Bronze Medal and Iran Joliot-Curie Prize, and many others that I'm not going to list here. So we're very happy to have her today. Thank you. Welcome.
Thanks everybody for coming. It's a pleasure to come to Boston and see my friends. I haven't answered any emails since 3 days essentially, so that's how busy you guys were keeping me. So that's really good. With many science ideas. But okay, about my talk. So I want to tell you about a line of work. Like, okay, these days most groups publish many papers, so and it's not always so easy to see a structure and the logic in them. So this talk is about a line of work that appears in the 6 now papers. They are all about attention, and the ones highlighted in yellow I will tell you a bit more in detail. But before I get into that, I have a part that is a bit more generic introduction, starting with scaling law, a picture that most of you guys have seen, that this was a bet, a key bet that gave rise to what we are currently witnessing in AI. And as compute and number of data and number of parameters goes large, we see these predictive and who knows where they are really coming from and whether they are necessary. So given that and all the progress that we have, the fundamental questions, for instance, is scaling the only way to go, or is there some much faster way to construct the AI that will do as well? We don't know, and evidence rather suggests that probably there is. I mean, one thing is that the brain doesn't use so much energy and data, so that would suggest that maybe there is a way. Another item that I see as an evidence of that is the whole humbug around DeepSeek, like in pretty irrespectively about what exactly they did, the fact that their claim of speeding up things by a factor 20, the fact that it shook the huge industry so much that people were truly afraid that this is true and that we actually can suddenly do it much more efficiently, to me is like evidence that we really don't know whether that's the best way to go about it. So this fundamental question, what are the statistical limitations given by how much compute is given and how much data we can measure, is essentially entirely open so far. So unlike in other fields, for instance, communication theory, where we had the Shannon capacity and the Shannon bounds on everything, and that was driving, trying to achieve them was driving the science. In AI, we are a bit the opposite. Great achievements were made without really having a good understanding of these fundamental limitations. And so with scaling, there are more questions that come. How do we derive the exponents? We have capabilities that emerge with scale. I don't know if Naomi is in the audience. I was talking to her about interesting work she has in that this morning. Is this a phase transition? How do we explain it? And the very curse of dimensionality, the fact that for worst case data, we know that the learning problem is computationally hard, whereas for the tasks on which they are working, there must be something particular, some particular reason for which we can actually find the values of the parameters that work efficiently. But what characterizes these tasks where the curse of dimensionality can be avoided and when really it cannot, we don't know.
So many questions. But the nice thing is that the scaling things up, making them large, also brings some answers, or at least some hints of methodology to bring answers. And I like the way David Donohoe puts it when he calls it the blessing of dimensionality. Within the right scaling limit, the concentration of measure allows us to describe the behavior in just few parameters, order parameters, as we call them in physics. And that's something that is very much present, very, very core of the high dimensional statistics. But in physics, that actually appeared a century ago, more than a century ago, and the very foundation of what the field of statistical physics is and how phase transitions in nature, such as water melting, are understood, is a manifestation of this blessing of dimensionality. Many people, they're okay. So this will be our tool to try to now take advantage of the scaling to actually use this methodology that leverages on the blessing of dimensionality. And in doing so, the way we will be doing so is, as is common in science, building simplified models. But now when it comes to building theory using simplified models, I like this caricature that I stole from Scott Pesme, that maybe the current AI theory can be seen as the paper airplane, while we are aiming at something that is AI once understood. Here I caricature it by the Airbus A380. Okay, so what? So we are far away, okay. But I mean, my kind of, I argue that going from the paper airplane to this is still the right way, because the current system today, it looks maybe something like this. And the brain, here we are in an institute that studies the brain, so maybe the brain as well. There are probably some artifacts that are there because of the evolution that don't really have to be there, so who knows. So I would argue that there are three ways to kind of proceed in the study, right? Either you start with the current system and you want to somehow distill it to the optimal AI once in the future. So that's a totally valid way of wanting to do it, in my opinion. Or you go from the purple A-plane saying, okay, understanding this path will be easier than understanding this path. That's kind of my hypothesis. That's how I aim to skip through describing the current mess and thinking that understanding the ultimate AI may actually be simpler. And then, the path from the purple A-plane to the current systems, many people, I think about it this way. I think we should go. I don't know whether this is so constructive and productive, because then we may be studying some parts that actually will disappear eventually. So maybe going this way, that's what I'm aiming at. So don't ask me the question of how what I do is useful for the current systems. Ask me how is it useful for the systems 30 years ahead or something like that. And there, hopefully, I can make some speculations that you also find interesting. So that's the philosophy here. Okay, now to make it a bit more concrete, what should you put in so that in your simplified model or AI, you are not throwing away the baby with the water, right? Some ingredients are essential, otherwise you are not even addressing the true question of the fundamental limits of learnability from data. So I find useful to think about the key ingredients. There are 4 of them, really. There is the model for the data, the architecture of the network that is learning, the estimator and the algorithm that is actually running to estimate it, and the large size limit. I've put the large size limit aside because at first when I started thinking of this triangle, I was not thinking about the large size limit as something crucial. It was more implicit, of course. To do statistical physics, I need some large size limit. But with the scaling becoming so important, it actually became a key part of the modeling of which large size limit are we actually taking. So from these ingredients, maybe the one that where people would perhaps implicitly not be taking it into account as a modeling aspect in the ML theory works are the models for the data and tasks, probably influenced by the early or the field of computer science where we want to prove things for all data. So we don't want to assume anything, or for the worst case data. Like assuming something about data seems like a weakness, like a limitation. But in machine learning, I argue that modeling the data is necessary, at least for two reasons. So one reason is that if we do not model the data, then we are saying something that is true for all data. But we also know that in the worst case computation complexity sense, the learning is NP hard. So the worst case data will make it hard. Whereas what is happening today is actually cases where it is efficient. So we would not be describing those cases where it is efficient if what we are saying holds for any data. And the second reason is if we are not modeling the data and the task, then it is very hard, or at least very indirect, to talk about generalization. Do we really generalize to samples that were not present in the training set? I mean, we need to have some idea of what is the task actually, what is the structure in the data. Okay, so once we accept that these four ingredients are the core ones that should be there, and the rest, okay, we will see, then we can aim at solvable models. When I say solvable, I mean that I'm able to use this blessing of dimensionality to write a closed form description of the statistical and computational limits. So, for instance, answer questions such as the generalization error that is achievable computationally efficiently for a given number of examples is this. Okay, so now there are some physics background people in the audience, so and I myself, and let's tell to those who are not, that there is a dictionary of thinking of these ingredients in terms of statistical physics of disordered systems. So if I say that the data and model, the model for task and data is structured disorder, and the architecture defines the interaction between my degrees of freedom. The degrees of freedom are the learnable weights. I may call them spins if I want. The algorithm is the dynamics. The high dimensionality of the input space, we usually call it the mean field limit. The large size limit is the thermodynamic limit. In this dictionary, these toy models become mean field spin glasses. And long time ago in the time scale of machine learning, this has been realized, and these references I give here, those are not even papers, those are actually books and reviews. This was a whole field that has books and reviews on, and Haim is here, and Scott's work on the basic spin glass models was very influential in that. Okay. So to go to some concrete things, like to start with the simplest case that brought useful insight along this line of work, I would go back to another pioneer in the field, Elizabeth Gardner, who suggested this data model, the teacher-student perceptron, where, maybe on this slide it's explained better, where we take inputs, X, that will be just Gaussian IID noise, so no structure in the inputs. All structured in the data as we are constructing it here will be in the function from the inputs to the outputs. And here we will be, the data model is generating the labels by taking some nonlinear functions, a sign or ReLU or identity, on a product between some teacher weights and the samples at the input. And we take the high dimensional limit where the dimension and the number of samples are both large and proportionally so. So this indeed has been done in Gardner's papers and other papers in this subfield in the 90s or even 80s. And in the field of statistics, the high dimensional statistics that takes this limit appeared maybe a decade or two later. So it was maybe not connected back then. So, okay, that's how we create the data. Now on a data like that, we can start studying how very simple neural networks, for instance, linear regression itself, just a single layer neural network, or comparably simple neural networks work. And now this seems like all extremely simple, but that's actually where the theory of deep learning starts, with linear regression. Like a lot of the progress that we have seen in the, say, past 10 years understanding phenomena that were motivating, but motivated by what is happening in deep learning. For instance, the scaling laws, the double descent, things about implicit regularization, learning dynamics, or overparametrization. They were all demonstrated on some kind of variant of this model of linear regression. So a lot can be done within this simple model. And here I just have slide collecting some like keywords about the methodology that was developed and that is being used in the context of understanding and proving things about behavior of these models. I will not go into the detail. And once, okay, you have the models, you have the methodology, then there has been a lot of works. I don't really cite any here, but there could be hundreds, that if I go back to my triangle that characterizes the ingredients of the models I should be accounting for generalized linear models and random features and kernel methods, and also a lot has been done for two-layer neural networks, so one hidden layer. On the side of the data, the influential lines of works were on this teacher-student model that currently is called rather single-index model or multi-index model, or generalized linear regression, or some unsupervised cases of spiked matrix models and Gaussian mixtures. So all these kind of you can view it as variants of this Gardner's teacher-student model. And the algorithms, of course, we are interested in the empirical risk minimization and behavior of GD and SGD in such settings, but it's also very insightful to compare to the base optimal estimator and to an algorithm that estimates that, the approximate message passing, that also serves as a proof technique to essentially look at all the rest in this high dimension limit. So, okay, a lot of works. I will just mention like one line of interesting realizations in all that I find very insightful. And my favorite example in that is the phase retrieval. So that's a problem in signal processing where, formulating it as this teacher-student model. So we create data using some random vector of weights and the Gaussian data, X. We create the labels just by making a scalar product and squaring it. So the squares comes from the fact that the phase gets lost, but here I don't want to work with complex numbers, but in real numbers, then hence the sign get lost. And then I observe pairs of X and Y, and the task is to find the function so that on a test set I can predict the right Y for a given X. So I really formulate it as a machine learning problem. So what happens in this model? If we apply the methodology of that was kind of just with references and keywords summarized on one slide, we can answer in this very limited and simple setting the fundamental question about what are the computational and statistical limits of what is learnable given a certain number of samples and certain time. So here, it's summarized in this picture for the phase retrieval. I have, as a function of the number of samples over the dimension, so that's the sample complexity, I have the optimal test error that is achievable. And the orange line, that if it is not visible, it's because it's covered by the blue line, is the optimal performance. And you see that it has two interesting points. One is at half, when it starts to be better than random guessing, and another one is at 1, where it jumps to 0. And another interesting comparison is the blue line, which is the performance of this approximate message passing that aims to estimate the base optimal estimator. It also jumps to 0, but a little later. And we understand precisely these curves and can prove precisely their form. I'm not giving the form, it's not like super insightful. But the point that I want to make here is that these three particular values of the sample complexity for the phase retrieval, they are phase transitions, really in the same sense as they are when water melts or magnets cease to be magnetic at the Curie temperature. So the one at half, that's a second order phase transition, it happens continuously. The one at 1 is a first order phase transition, happens discontinuously. And the one at 1.13 is what we call in physics the spinodal of the first order phase transition, where the metastability disappears. And we can really make an analogy to the physical systems where liquid that can potentially be supercooled or become ice corresponds if we say liquid is the impossible phase and I is the phase where perfect generalization is possible, then this hard phase where the algorithm doesn't work, but it is possible information theoretically, is the supercooled liquid. And anytime we have a first order phase transition, it is related to this hard phase, this metastable region. So first order phase transitions are associated with computationally hard metastable phase. And this, there has been a line of work in computer science where people aim to make this claim more and more precise in a broader and broader range of problems. So from an example like that, that's just one example, but the same picture appears in many other examples. So we can start thinking of a kind of phase diagram as the number of samples is growing or as the signal to noise is growing. It may be quite generic that at small, whatever this number is, it's impossible to learn, and then there is a statistical threshold where it becomes possible but not computationally efficient to learn, so hard to learn but possible. And then there is a computational threshold where it becomes also efficiently learnable, and then maybe somewhere later on the standard methods will start working. So the takeaway is that the fundamental statistical and computational limits that we would love to understand in general, we are far away from that, but under very restrictive assumptions in these simple models, we can today understand them in quite a detail, and they are given by phase transitions and their spinodals, and locating them also allows us to understand how the state-of-the-art methods or the standard methods are from the optimality under these settings. So that's useful. And now when it comes to the standard algorithms, not approximate message passing by gradient descent, just 2 more slides. Like there is a still very interesting takeaway in this phase retrieval. So first, let's just compare the performance of gradient descent to the approximate message passing. Gradient descent minimizing the natural loss for phase retrieval, that here would be just this. Like we know that the labels were created making this product and squaring it. We just don't know what the vector of weights was for the teacher. So we construct a loss where we put some vector of weights and minimize over it. So this is a non-convex loss, but we run empirically gradient descent, and we see that it actually, this approximate message passing algorithm started working, perfectly generalizing, starting from sample complexity 1.13. And if we do the same thing with gradient descent, we actually need much more, 7, and this is probably actually going as a logarithm of, not probably, this is actually growing with the logarithm of d, so this is 7 for the sizes that we were able to simulate. So, but it's much worse, that's the takeaway. So what's going on? Why would we be using in machine learning gradient descent if in such a simple but not adversarially constructed, like typical high-dimensional problem, it's actually not working very well? Well, the answer is that in practice, we are actually not matching the loss to what we would maybe even know is the true model, that in this case, we know what is the true model that generated the data. We are over-parameterizing. We are taking the neural network architecture with many more parameters than necessary. We know that many of the models that we train, we can then compress them, and we don't lose much on the performance. But if you want to train them directly in the compressed form, it's not working. So there is something important in the overparameterization. So let's try it here. Let's take a loss function that simply adds a somewhat wide hidden layer. We are not changing anything about how the data were generated. So we are mismatching as a physicist who wants to model the real world. Here, I know there is only one vector W that created the labels, and here I'm modeling it using M, where M will be bigger than D vectors. So that somehow doesn't make sense. but let's try it nevertheless. And we can prove, and that's something we have done in this paper, that if we do it this way, then gradient descent will actually need only twice the dimension of samples to start working perfectly. So it gets much better than in the system where we would not overparameterize. There is still a little gap to the approximate message passing, but the bottom line, the takeaway, is that it's really the overparameterization and the dynamics of the gradient descent that here play together to reduce the number of samples needed to learn this particular task well. And the overparameterization helps the gradient descent to overcome the curse of dimensionality, not only in the sense that it smoothens the inertial landscape, but it does it while not losing the ability to generalize. And this, to me, is a nice, simple example where this can be demonstrated very concretely. All right. So to go on, okay, today, who cares about multilayer perceptrons anyway, right? Okay, this was a single layer or maybe one hidden layer, but okay, we could ask ourselves, can we do more layers? But who cares anyway, because isn't everything about transformers? And that's where I come, finally back to the main topic of the talk, that is to say something about generalization ability through attention layers. So now it seems like I completely changed the topic in the talk, right? Now I was talking about perceptron, nothing about transformers. So not so much, right? I will not be changing the tools so much, but let's, in order to see what we will be doing, let's first summarize, at least from my point of view, what are the key differences between simple models for feed-forward neural networks and attention. So what is there different in learning with transformers? And I have 3 points. Like one difference is, I wonder if I can, it's kind of bothersome that you can't really read things. Like that is a bit small. So one key difference is that we tokenize the data. Why? Okay, I'm not really sure, but that's what's happening. That instead of presenting vectors at the input, as in feed-forward neural networks, we are presenting sequences of vectors, we call them tokens. So still d-dimensional vectors, but t of them instead of one d-dimensional vector. So okay, so maybe that's one aspect that we will want to put in the models on the side of the data, right? That you have sequences of tokens. The other thing, now I touched this. The other thing is that we are not training in a supervised way as before, where we had the labels explicitly divided from the inputs, but in a self-supervised way. For instance, by next token predictions or other ways of self-supervision. For instance, adding noise and denoising in generative diffusion. And the third is that next to the fully connected layers, which are still there, but they are interlaid, they are applied token-wise, so for each of the tokens, and they are interlaid with the dot product attention layer that mixes the embedding dimensions through this value and query and key matrices, but then also mixes along the token dimension through this attention matrix, multiplies by a t by t matrix. So that is different, okay. And we are training these 3 matrices, not only this fully connected matrix of weights as in the fully connected layer. So to me, these are the key 3 differences. And okay, there are many others, but maybe the others are, okay, the hypothesis is that I will start with including these ones, incorporating these ones, or at least 2 of them, at least in the talk today. And how do I do that? Well, I don't have to start from scratch, right? I build the strategy. I build the strategy by saying I have the 3 ingredients and the limit, 4 ingredients, the limit is part of it. So I just have to think now with what changed, what is really what I have to change in my ingredients. And what is nice about this line of work where progress has been made along the 3 different axes is that most of the time when progress is made along one of the axes, it's actually compatible with what has been done along the other axis. So to me, this like high dimensional approach to toy learning models at least has that property that sometimes when I look at on the archive on random papers on learning theory, okay, maybe it's because I'm not one of the authors, but often it appears to me that there are kind of random settings, like, okay, some question and a setting that gives some element of an answer in it, and then months later, the same group of authors, completely different model on a different question, and they seem not so related. So I'm asking myself, okay, so how is this leading to some progress that is built one on the previous kind of successes? So at least in my head, I don't know if it is so visible from the papers, in this approach, it's actually everything building on each other, and progresses in multiple directions can all be put together and used together. So I just kind of need to continue along improving the models, but now including the structure sequences of tokens on the side of the data models, and include the attention on the side of the architecture, and include the self-supervision on the side of the algorithm. And now in the large size limit, there are multiple parameters that can possibly go large, but at least the two that have to do with the size of the input, the context length and the embedding dimension, I have already 3 ways into which I can take them to infinity, even both together, or either both together, or one of them large and the other small. So that gives me 3 possible limits. So all these cases are to be explored. In this talk today, I will still stick to supervised, so no self-supervision today. I will include the attention and the sequences of tokens, and I will work in this limit where the context length is of order 1 and the embedding dimension is large. Okay, so in practice, the context length is large, and this, oh, okay, it's still working, is large. So we would more want to work in the third case where both the sequence length and embedding dimension is large. But okay, one needs to start somewhere, so already including 2 of the 4 things is not too bad, at least in my opinion. Okay, and last kind of generic slide is about a bit of a word of a caution of how I am using the word model, because I feel that always causes any confusion because I use it in 2 different ways. In machine learning, we mostly mean by model the neural network, the model that is then trained and that gives us the estimator. That's one of the ways I'm using it, but I also have the model for the data. I assume that there is some caricatural ground truth world that generated the data and that I have some knowledge of this world. And that's also a model, but not the one that is learning, the model of the data. So there's the teacher, the model of the data, and the student is the neural network that is learning. And then, of course, where the confusion comes from often is from this ingenious but perhaps a bit confusing idea of Gardner of actually making the teacher to have just the same form as the simplest student, right? So they look like mathematically it's the same equation, but it's very important to distinguish which one of them is generating the data, the synthetic toy data, and which one of them is then learning on the synthetic toy data. And they, of course, do not have to be the same. The case when they are the same is the simplest one to analyze. We often start with that one, but in those that I will be showing you today, they're actually not the same, but related, of course, because the model that is learning needs to be related to the structure in the data so that it works. All right, so learning from sequences of tokens. When I will describe the models, now we have 3 indices, right? There is the index that describes the sample, that I will call mu. There is the index that describes which token, that I will call A. And there is the index that describes where I am in the embedding dimension, that I will call I. So when things will not be matrices or vectors and will have indices, the indices will always mean this. Okay, and now I'm finally back to the list of the papers I want to just describe. So they are clustered here by 2 slightly different models. One that we call the sequence multi-index model and the other that we call the attention index model. So I just want to define these models. So let's start with the sequence multi-index model. That one actually looks pretty similar to this simple Gardner teacher-student model. I will now have a couple more vectors, W star. I will index them by B. B will go from 1 to P, and little p will be the number of indices. When I say multi-index, there will be number of indices. So each of these vectors, W star, is one index, and I have P of them. And they all multiply the input data along the embedding dimension. Okay? And then A is the token index running from 1 to context length that I consider of order 1. And the embedding dimension number of samples will be large, proportionally so. So this is what I'm generating the labels this way. This is what I will call sequence multi-index model. So it's similar, related to the previous model, except that now I have t times p of those arguments in some ground truth activation function. So I just have many more indices in my equations. But if you know something about how the methods work for the single index or multi-index model, these indices will probably not scare you. You will somehow see that, okay, some of my vectors will become matrices, but small ones, so I will be able to deal with it. So the message here is that in order to study a model like that, we can completely leverage all the same tools as we were using for the multi-index model. That was kind of the previous chapter, without sequences and without attention. And in those cases, the tools gave us powerful lens into the learning dynamics and generalization. So the goal here is, or the hope here is that it will be the same. And here I just list some special cases, but so far you say, okay, sure, I can generalize this way. But so far it doesn't look like, okay, maybe there are sequences because T is the context length, but where is the attention, right? So far, like written like that, you don't see the attention there. Where is it? So it actually contains many special cases, right? If you read these special cases here, for instance, deep attention only model with low rank key and query. So how does that look? What I mean by that? So I'm still thinking in terms of like how I generate the data. So let's say that now I still take the inputs IID Gaussian, but now the label, the target function, is more complicated. I have, say, L layers of applying something like this. So this is a skip connection C. Sigma can be a softmax. Usually it is in the attention. And here I have the form that I usually put in the attention, in the self-attention, with the simplification in this particular paper where we actually tie the key and query. So the key and query matrices are the same because, okay, we are not really, at the simplification of the model, it will not matter here whether they will be untied or not. So for the generation of the data, I tie them for the learning as well. But otherwise, you see that the structure resembles attention only in each layer. And here I wrote it for a single head in each layer structure that generates the outputs. And now, okay, now one needs to like sit for 15 minutes and go through Appendix A in the paper to actually see that indeed something written this way can be written in the form on the previous slide. And the number of indices P will just be the sum of the ranks of the keys and queries across the layers. So as long as these ranks are of order 1, the final number of indices is order 1, and all the equations that we derived generically for the previous model will apply to this one. So that's one example, the first model. And the second model is very similar with one add-on, that is that the rank of the key and query will not be small. And in practice, they are not small, right? The practical rank of the key and query, or rank the width, is taken something like the embedding dimension over number of heads for many of the architectures for some arbitrary reason or something of that kind. So it is rather of the order of the embedding dimension. So in the second model that we call attention index model, we want not to have to restrict the rank of the key and query. And in order to do that, we will still consider the kind of multi-index, so function applied to multiple variables, where each variable, we call it an index. But this time, it is not a linear index, it is a bilinear index. I have W star, and multiplied by X from right and left, as it is in the attention layer. So indeed, you realize, or may probably already realized, that what the attention is nothing but a bilinear form on the data. So so this will be crucial also then to realize actually what this type of model is, because if I consider the key and query multiplied together and the data times the other token as a kind of data concatenating matrix, then a structure like that becomes just a trace of product of two matrices, where one of them, the one coming from X, is known, and the other one, that's the ways that I'm training. And this is something that also in the high-dimensional statistics or signal processing theory literature, this is something that is called a matrix sensing problem. It's again a problem that has been studied that is similar to the linear regression. The compressed sensing would be the linear regression, and the matrix sensing is an analogous problem where instead of inducing, for instance, sparsity directly in the parameters, we induce sparsity on the spectrum of the signal matrix. And it's a class of problems around which there is a rich literature and the high-dimensional phenomenology, including the approximate message passing, and this method has been developed. And here we realize that the attention layer is essentially a special case of the matrix sensing. We just need to add these token indices again. But there are only a finite number of them, so that again will just bring some more indices in the equations. Yeah, question?
A quick question. Is this supposed to be a nonlinearity, or are we missing nonlinearity in this model?
So here, this is the model for how we generate the data, and this f star is an arbitrary function of this t squared times p variables. And the f star can be anything. And for instance, before, to write the L layer attention only as the sequence multi-index model, the form of the S star was very bulky, like the mapping is in the form of the S star. So here I'm like hiding, all the richness or not all, but a lot of the richness is largely hidden in the form of this F star that is a function of t squared times p parameter. So that gives me a lot of freedom to make it, to consider few layers and heads and this and that, and follow the attention with the random features MLP, or a lot of kind of things that can be written in this form. So the nonlinearity is in the F star, but this is the generation of the data. So there it may be not so crucial. It's just my toy case for like what the data are. The softmax in the attention will be then in the model that is learning on the next slide, I believe, or 2 slides from now. Okay, so the key message is that it boils down to be matrix sensing problem. And it accounts for the extensive Rankian query that corresponds more to the sizes that are used in practice. And now, okay, given the definition, now the methodology becomes the same thing as before, and going to the details that would take multiple lectures. So the core message here is that for the sequence multi-index model, it's really just the multi-index model from the methodology point of view, more or less. And for the attention index model, it's really the high-dimension analysis of these matrix sensing problems with the indices added to it. So it's a little bit more annoying, but not fundamentally more. And so on the next few slides, I just wanted to summarize, maybe there are 2 interesting aspects of what is particular in the methodology here for the attention index model. So one is about the mapping to the matrix sensing problem. And I will explain it actually on a quadratic neural network. So no sequence is going back to just single hidden layer network with quadratic activation. That's the neatest case where it can be seen. That also maps actually to the matrix sensing problem for the same reasons. So here I'm creating the labels with the R hidden neurons, quadratic activation, one hidden layer neural network. X is the data, W star is the teacher weights. That can be rewritten like that. And learning with empirical risk minimization of the same form. Okay, so let me just rewrite it. What is the target? Just rewrite it once more as a trace of one matrix times another matrix. One matrix that depends only on the data, so it is known, this Z, and one matrix that depends only on the weight, so that's the matrix, that's the signal, the unknown matrix that is adjusted in the training process. And the first key property here is that even though this matrix Z looks nothing like a random Gaussian matrix, right? If you were to write it and look at its spectrum, or you would immediately realize that it's not a Gaussian IID matrix. For what concerns the generalization error of the learning model, it is the same in the thermodynamic limit, in this high dimensional limit, as if this matrix was a Gaussian IID matrix. So that's curious. That's one of these Gaussian universality theorems. That actually something that is not Gaussian behaves as it was for what concerns, some ways of measuring it through, in this case, the generalization error of the corresponding learning model. So that's one interesting property. It's an interesting Gaussian universality. And the second is what actually the L2 regularization on the weights becomes, because the S matrix was just the weights times transpose of the weights. If we put Frobenius norm on the weights, it becomes a nuclear norm on the S. Okay, so the weight decay on the weights in the matrix sensing formulation becomes the nuclear norm on the S matrix. And that's the norm that induces low rankness, right? It's like L1 norm on the spectrum. Okay, and for the nuclear norm on the signal, we actually in the matrix sensing literature have the appropriate algorithms, the approximate message passing, and their state evolution. One just needs to account for this regularization through a denoiser that in that case is just soft thresholding on the eigenvalues of S rather than the usual denoisers in the AMP, say for in linear regression. So, okay, here I'm going a bit more for the people who know about these algorithms. For the others, that's very cryptic, but you can skip it. It's not important. Just wanted to say a little bit like 2 snippets of what is technically different here. And with that, once you go through these 2 technical novelties, you end up with equations that describe the test error as a function of the sample complexity of a noise. And in order to recover what this delta parameter is, you just need to solve 2 equations that have this form, 2 equations because there is one additional unknown epsilon. So you solve for delta and epsilon. And this function is some curious function where you take the spectral density of a random matrix that is the teacher signal plus a Gaussian random matrix, and its spectral density, you take some integral of that, and that defines this function JAB, and from that you solve for your generalization error. So this is the blessing of dimensionality kicking in, right? Here, this was a high dimensional problem, number of samples that was quadratic in the dimension. And here I described it in the thermodynamic limit, and under the assumptions that I'm showing, the test error will always be this, where delta is a solution of these equations, and all the quantities in these equations are scalar. So no, I put the high dimensionality away. Okay. So now again, there's the list of the papers, and now I will tell you, given that, given the equations that correspond, what do we actually learn about the single head attention in high dimensions? And this is, again, how I generate the data. So it's the output is an output of a single layer, single head attention with tight keys and queries. So all these simplifications to just create a case where, there's the simplest one where things get non-trivial. And and in the limit that I was stating before. So I generate the data this way, present the x and y as a data set, and learn it how? Learn it using a related architecture with a loss like that, weight decay of the usual form, and a single head, single layer attention with, again, tight keys and queries. So I match the architecture, but I'm looking here at the minimization here. So what do I get from that? What will be the... So first observation that is interesting is I was telling you how the weight decay becomes the nuclear norm. So here that's the same. The weight decay on the keys and queries becomes a nuclear norm on this matrix where we multiply the keys and queries that are tight in this case. And that alone induces the low rankness of what here? The keys and queries. And that alone already gives us, now we need to work a bit to write these high-dimensional equations to put in mostly these token indices, otherwise it's the equations that I showed you already. I will not be showing you that as they are not super insightful, but their behavior is interesting. So for instance, what you can compare here is this kind of naive question that you could ask. Why in the attention are we actually training the query and key separately? Because if we multiply them together, this would create a matrix D by D, and we could just train with respect to components of each component of this matrix directly. We could run the gradient descent with respect to those components. And okay, this is never done in practice. You will understand shortly why. But in a lot of in numerous theoretical works that study attention, this is actually done as a simplification. Let's not separate the key and query. Let's assume that the gradient descent is run with respect to each element of their product. And you should not do that. And you will immediately understand why if you understood how the nuclear norm appears and what's the role of the nuclear norm. Because the nuclear norm induces low rank, and if a low rank implicit bias was important for your task, then training it the usual way will be good, and training it this alternative way on the unfactorized key and query will not be good. And here I'm comparing the property on our model. So for instance, the test error, if you factorize, is good, and if you don't, it's much worse. And you can collect it in a kind of phase diagram where if, depending on the width of the target function, if it was really small, then by factorizing, you win really a lot with respect to the case where you would not be factorizing the key and query. So this is like a first snippet of an insight that, you know, it doesn't tell what the practitioners should be doing because they were never doing it in the first place, but it at least explains that why it should not be done, that you train the product of the key and query, and why, if you are writing a theory paper where you're assuming that, you should be careful whether this is maybe not like changing the results that you're obtaining. So if you consider gradient descent directly on M, be careful. Okay, and then the theory also gives us access, so to the test error. I already showed you some plots of the test error. But what is interesting is that in terms of the same order parameters, these two numbers, delta and epsilon, we also get access to the spectral density of the key and query matrices. So this is something that one can measure in practice. What is the spectral density of key and query matrices? You know, what to draw from this is not as clear, but at least a reasonable model should reproduce the similarly looking spectral densities. So that's exactly what is happening here. This is the spectral densities from our model. In the next slide, I have the ones observed empirically. But what is even more interesting maybe is that both these are analytical formulas that are written in terms of the same two order parameters. So there is a clear link between what part of the spectral density of the key and query plays which role in the expression for the generalization error. And this is something that, okay, it's a bit difficult to see it from the equations, but one can numerically separate these different contributions. So if here below is the spectrum of the target function, so that's just imagine that there's the blue and black together. And then the empirical risk minimization with some sample complexity will get a spectral density that is a bulk here, that is like a semicircle bulk or Marchenko-Pastur bulk, and some outliers in green. And you see that the outliers in green are somewhat aligned with the black, but not exactly. That's the statistical error, the fact that you have finite number of samples, so you don't get them exactly. And the really small ones, they are hidden in the bulk. So, and now you can say that that the test error can actually decompose into a contribution that comes from the that comes from the approximation error, from the overfitting, from the underfitting. You know, one comes from the mismatch between the black and green. One comes from the fact that some of the blue are still hidden in the bulk. And we have this somewhat neat decomposition of the test error in terms of the property of the spectrum. So we found this nice, that this is somehow if this was true in practice, this would be a bit of a holy grail. So this is not yet clear, but at least in this model, we have a specific relation between the generalization error and the spectrum of the learned matrices. And it's given in terms of the same order parameters we can trace back in the equations which term plays what role. So here is the slide where I show you how the spectra of the Keys-and queries look in practice. So this plot on the left is actually for the quadratic networks, or not for quadratic, for fully connected networks. And on the right, these are for simple transformers like BERT and Llama. So you see that now, depending on the task and how exactly you're training, some of them look very much like the ones we are obtaining in our model, that there is this bulk, Marchenko-Pastur-like, and then another bulk that is either bleeding out or disconnected from this bulk due to the noise, and in the transformers is similar. But then in other cases, there is actually something that looks like a very heavy tail of these larger eigenvalues. There are fewer of them, and the bulk and the outliers are maybe not a bulk, but maybe just few of them separated coming out. So this is this is the practice. This is papers that measure these spectrum of Keys-and queries or the weight matrices empirically. So now question to inspect whether our model is reasonable is, can we actually observe, for instance, this heavy tail decay as one sees in the practical cases? And it's really simple actually to make it so. What do we need to do? We assume that the target function, we assumed it in this form with some target signal S star. But before, we were just taking the S star as a product of two random matrices, right? Just random Gaussian matrices. Now we will take it from a different ensemble of random matrices. We will take it's a random matrix such that the spectrum of the eigenvalues has a decay, has a power law decay with exponent gamma. We impose that in, and then we train in the same way as before. And we ask ourselves, can we extract from the equations that we have for the test error, how fast will the test error decay? Or will there be a power law decay or not? And if yes, then what will be the exponent? And we see that this will depend on the regime. This will depend on how much we regularize and how many samples we have. And in some cases, indeed, we get a power law decay with a non-trivial exponent that depends on this exponent gamma. So this theory also predicts the test error scaling law of the gradient descent at convergence, and the spectrum of weights mimics, in that case, those observed empirically with this kind of power law of outliers bleeding out. And when I said that it depends on the regularization and the number of samples, we actually get this relatively rich phase diagram with 7 different phases, where some of them are not actually in the decay, and some of them is actually not a power law at all. It's just something trivial, either constant or 1 over n or 1 over square root of n. But in some of them, in this one and this one, the decay actually depends on the exponent, on the non-trivial exponent in the data. So that would be how the power law decay in the data translates into the scaling law of the test error as a function of the sample complexity. So one of the scaling laws in this Very simple setting. But the non-trivial one in the sense that think, okay, maybe they are more recent, but except these two works, I dare to say that all the other works you have seen on scaling laws of this at this level of theory, where the exponents were explicitly derived from first principle math, they were all some kind of variant of a linear or kernel methods. So those that truly non-trivially learn features, and here they do indeed. Even the spectrum at the initialization, it's random, just marching capacitor. And as we are training, the spectrum completely changes, becomes non-trivial power, looks like the one in practice, and the coefficients are associated to this. So these two works, or two, maybe I'm missing one, were for the quadratic null networks, but here, because that's also matrix compress sensing, the attention is also matrix compress sensing, the phase diagram looks essentially the same. The indices from the tokens do not change things drastically. Okay. So I'm back at my paper list, and how much time do I have? I have one more little story about the statistical advantage of softmax that I can happily skip and conclude. Or it can make what's 5 minutes?
That's perfect.
Okay, it's not a technical one. It's just like, okay, let's go for this one. So this question, is the softmax needed or not? This is a question that has been motivated in the empirical community when the state space models appeared. The state space models, they are kind of alternative to transformers, where the mixing of tokens doesn't happen through the attention layer, but happens differently through a layer that is actually linear. So that raises the question, is that enough? Could it be that the nonlinearity just in the MLP layers is enough, and actually the layers that are mixing tokens do not need nonlinearity, and this can still work equally well? And okay, somebody is saying no. And indeed, I mean, okay, there may be many reasons, but one of the reasons that was put forward that is very nice comes from this blog by Kamrat, who puts forward this task called needle in the haystack, where you just hide little information in a long text of unrelated information, and then you want to retrieve that information back. Your prompt is to retrieve that information back, and you have to hence search where in the context it actually was. It's hidden in a long context. So that long context is the haystack. The needle is that information, like for instance, Lenka today is speaking at Kempner Institute, and you ask the prompt is, where is Lenka speaking today? It needs to search for the Kempner Institute in this long context. So that's the NLP task on which it was demonstrated that indeed the transformers using softmax do really well, and the state space models fail or do much worse. So we wanted to have a version of a single index model or sequence multi-index model that actually mimics that task, that needle in the haystack task, and in which we can see the same advantage of the softmax with respect to the other cases. So, okay, that's the evidence that the softmax makes the needle visible in a way. But the theoretical evidence about the advantages of softmax was not there. And again, a similar cautionary tale was that actually many theory papers consider the attention linear. So for some tasks, this may be fine, but for some other tasks, this may actually be losing on performance. So again, one needs to be, it's not like uniformly wrong, sometimes it's totally fine, but one needs to be very cautious whether assuming the linearity actually is not making it lose the ability to learn what we wanted to learn. So in this case, let's formulate this needle in the haystack as a sequence multi-index model, and we formulate a data model this way. So it's essentially a linear regression. Like in linear regression, you would have data and you would multiply by a teacher vector. This would create labels. But here we say there is the context length, and all but one of the tokens are just Gaussian and are not creating the label. And there is only one of the tokens, the epsilon star index token, that creates the labels. That one is special. And we have two variants of the model, but let me explain the second one. That special token is actually given a bias along the direction of a vector k star. So we take a little spike along direction k star, and then add a lot of noise to it. So that if you're just looking at the t tokens, we don't see immediately which one is the biased one. They all look very much still Gaussian. But if we had k star and did a scalar product, then we would see. Okay, but k star is not given to us. We know that there is some k star, but the vector, the realization is not given to us. So then what very simple transformer, overstatement to call it a transformer, but say attention containing simple neural network can be trained to solve this task. Just this one. So it's a kind of, so it's a regression with the K, the query matrix of rank 1. So here I go back to the low rank case. And V, the value matrix. So here I have this Z, that's the place where the value usually is. Sigma will be the softmax or not. The argument is just the data times the key. In these search tasks, we don't need to really compare tokens to tokens. So we don't need self-attention. So we can say that the query is fixed. And then it gets hidden in the normalization of the softmax. And then we don't need to consider the query. So this is a model where we don't even need self-attention, just attention. And then let's compare softmax with other nonlinearities, kernelized attention, etc. And again, we work, write the equations, solve them, get the curves out of them. And then we see that in this case, this is actually the population losses. This is a different length of the context. And the y-axis is the performance, x-axis is the signal-to-noise ratio, how strong this spike was as compared to the noise in this special token. And we see that the lowest curve here, that's the Bayes risk, is the black curve. And the red curve, that's the performance of the softmax. They are actually the same in this case. And the others are worse. And as the context length is getting larger, the separation is getting larger. And this all kind of makes sense because if you didn't put the softmax, makes you point to the special token. And if you didn't have the softmax, rather were linear, you would have to be averaging over all the other tokens. So the more you have, the more effective noise you would have, and hence you would not be able to reach the Bayes optimal performance. So it's intuitive why in this task you actually do need the softmax, and we can like fully solve it and write all these things as theorems. So this is kind of, at least I found it nice. So I will stop here. Let you stare at this diagram. Like if we model the data and the network and the algorithm and do it within this framework of high dimensional, let's call it spin glass theory, or that's if you want, or whatever else, then we are in a way like the important thing is that any progress is compatible with the progress in the other directions. So we are actually hopefully building something eventually that will allow us to describe these fundamental limitations, the computational and statistical ones, in uncover some principles that so far stay buried in what we don't understand about these systems, and some more like immediate items on which we want to look at is to put more structure among the inputs and correlation between the tokens and look at properly at the dynamics of these models. So far we were looking at the global minimizers of the empirical risk and just numerically comparing to the gradient descent, and saw that the non-convexity acts in a more or less benign way, that we always reach these global minimizers empirically, but it's not properly shown within equations. And we can look at many other things. The one that I'm excited about is to start thinking, but many people did, about memorization, but desired memorization. How do we actually at the same time memorize facts and learn rules within the same architectures, and again within this class of models. So I will stop here. I hope this was not too much.
Questions?
mentioned on the last slide, adding MLPs. What would it take to do this? Any thoughts?
Yeah, so it's kind of a curious fact that here the way the attention is organized and in the limits of short sequences, I can actually deal with 10 layers, no problem, of attention only. If it coming back to the multi-layer perceptron, even with a single layer, I told you about quadratic activation, right? Why did I insist on the quadratic activation? Because that's the only one that we understand properly enough, at least, okay, I understand properly enough. And maybe I should define properly enough, meaning that the progress that one makes on the architecture side is really compatible with all the other methodology, right? So I need some property of actually the solution that currently we don't have unless we look only at the quadratic activation. So even for cubic activation or ReLU, with just single hidden layer, if both the student and the teacher have the structure, we don't have the analogous theory that would be clear enough to be able to reduce it. So that makes me unhappy, and that also blocks the progress in terms of adding the multi-layer perceptron, say like 5-layer perceptron between the attention layers. So far so it's a technical problem. And what we are able to do so far, we are able to interlay it with a kernel method, with a linear method, or random features. So that for many things will already be enough, but not yet the multi-layer perceptron in a form in which it actually appears in practice. Oh, go on.
I'm thinking a lot of the theory work on analyzing transformers. There are various assumptions that we kind of ignore things like not just the NLPs, but I don't know, things like layer norm, RMS norm, residuals, also the tweaks that are there in practice.
I don't necessarily ignore that we have them in. It's just that in the particular works I was showing they were not consequential. So, but the layer norms, for instance, yeah, absolutely, those we don't account for. I mean, to me, that's, that goes back to that picture with the paper airplane and the horrible airplane and that. And also, but more seriously, to the fact that when we conceptualize on what data we will actually be looking at the performance of the neural networks, right? All these ingredients are there for some reason. And that reason may not be relevant for a given data set. So in the cases that we looked at, it didn't seem like these are crucial, right? The gradients were not exploding, they were behaving well, but there was just one hidden layer after all, so it was not so bad, right? So each of these elements have their role, and the way I kind of see a continuation of this work is precisely identifying the minimal ingredients in the data that actually require these ingredients, right? Not for like completely generic data, because then, okay, without those ingredients, it works better. This, I believe the practitioner colleagues that tell me that, but we don't know really like fundamentally why they are there, right? For me, a lot of the time, the papers that describe why they are there are not really convincing. Like it could be that or the opposite. I'm not like fully convinced. And I feel that if we go to much simpler settings where we can really scrutinize the full phase diagram and see, is it true that really, however we set the hyperparameters, they will still be needed? Or is there some region where they will be needed? Right? In a similar sense, if I go back to this scaling law phase diagram, so this is a simple setting, right? And then you would say that in practice, we always see scaling laws, okay. But in practice, how many samples do we have and what is the regularization that we use? Okay, I'm not like doing any one-to-one matching, right? I can't. But already in this simple setting, I have many possible behaviors of how the test error can decay and crossovers from one to another. And even in this very simple setting, there is not just one scaling law that I always see. It depends on the details And it's already a very rich structure, even in such a simple system. So it will be even richer in the real systems because there I have 100 parameters that I can tune, right? And kind of looking, oh, in practice, I need layer norm. Yeah, okay, but under what conditions, right? So if we are hoping to get that kind of understanding one day, I argue you just need to start with settings that are stripped from a lot of the complications to really identify the reasons truly, not just like waving hands and saying, oh, in practice it worked. That's great that it worked and you can make a lot of money, but what about the science, right? That's not yet there.
Thanks so much for the talk. Maybe just I'll follow up on what you mentioned right now. So, I mean, with these sort of families of models and this style of analysis, it really helps us understand sort of some of these features in a simplified way. But in your experience, do you see these models also helping us predict what would happen in empirical systems, right?
Right. So I don't see it yet because it will happen in 30 years. I mean, okay, I say it jokingly, but only half jokingly. No, because I mean, yeah, the complication of the current systems, yeah, that would be great, right? But I'm afraid that, and if I'm afraid that insisting on wanting to do that immediately may just lead us astray of the really interesting directions that will lead to the real understanding eventually. So I don't think as a community we should insist on it so much. Like if you can do it, that's amazing, right? And you will be very like wanted. But if you cannot do it yet, we should just recognize what science actually is. That's at least how I think about it.
It sounds like a great place to thank Lenka again.